All right, well, good afternoon, everyone. Thanks for coming. I'm excited to go through my presentation today, which is talking about heat pump designs, an award-winning one that achieved 450% efficiency, which is pretty impressive. A lot of questions already. I'm from the UK, as you can probably tell. This specific project was air to water, like all hydronic, but the concepts all apply to air to air too. And the things we go through are all using an air-to-air system as an example. So yeah, thought I'd just mention that. It might be on everyone's mind. Cool, so this heat pump specifically, 450% efficiency means that in winter, or even during winter, it consistently turned 1 kilowatt of electricity into 4.5 kilowatts of heat output, which is pretty hard to do. We'll say it's hard to do. Most people don't know how to do it. This presentation is all about showing you that it's not actually that difficult. It just requires you doing a few steps that, being used to installing furnaces and just gas systems, you'd never had to do some of the steps that we'll go through today. And yeah, it's all pretty straightforward, actionable steps. And if you follow them, you can get close to this efficiency yourself. And the idea is by the end of this presentation, you can go away and be able to implement it on your projects too. So yeah, a little bit about myself. I've been a mechanical engineer for the last 13 years, and the last 3 years, almost by accident, I've been like wholly or solely focused on heat pumps. Spent a lot of time in the US, in Australia, and obviously from the UK too. So I've not always been in the UK, but the company I work for does a lot of work in the UK, and during the last 3 years, we've seen the good, the bad, and the ugly with heat pump designs. And I suppose the government's been pushing it for much longer, so they're a bit further ahead than it seems like the US is starting out now. And a lot of the talks today have actually been quite reassuring because everyone's talking about the right things that the UK and Europe just messed up in the past. So yeah, we're going through those. And if we just take a look at the journey over the last 3 years, back in 2022, general consensus, especially amongst the public, was that heat pumps just simply don't work. Overall, no one was having a good experience. In 2023, the consensus shifted slightly. So some people were having successful heat pump designs or installs. So some people were happy, but there was still a lot that weren't working, and there was still a lot of doubt about heat pumps. However, in 2024, it's overwhelming now how much evidence there is of how to install a well-designed heat pump that achieves what the client wants. And yeah, I suppose all the benefits that come with a heat pump are possible. So living in comfortable temperatures, reducing your impact on the climate, and lower energy bills too. And this is the journey I've been on over the last 3 years, and that's why I suppose I'm here today to give a presentation of from seeing what wasn't working in 2022 to what's working in 2024. I'm pretty convinced all the people I work with who design award-winning heat pumps, there has been more than one. This is just one example. I know what they do that separates them from the 99% that I suppose don't achieve good heat pumps, and probably more the ones like back in 2022 are giving the clients heat pumps that, I mean, on the face of it, don't work. So yeah, the perfect example that we're going to be going through of all of this is how I worked with the award-winning heat pump installer, Mark Denman, to install the award-winning heat pump design. So this is the one that got the 450% efficiency. And the main bulk of this presentation is going to be looking at what Mark did to achieve great results, and also comparing it to, what I've called the average installer would do, but it's more what somebody who's not too experienced would do, and how that does cause problems. So it might be quite surprising to hear, but to achieve this level of efficiency, it's quite straightforward, and it just comes down to something that you're already doing, and that is, you've probably heard it time and time again the last couple of days, but it all comes down to your heat load calculations. I bolded and underlined accurate because that is the key here. You can do a quick heat load calculation, but if it's not accurate, the efficiency just falls off a cliff. So if you oversize, use rule of thumb, be a little bit conservative, it's all just going to be a really low-performing heat pump system. If you oversize enough or undersize enough, essentially takes you back to the 2022 examples I was seeing where people hadn't done accurate heat load calculations. So oversizing is just as bad as undersizing when it comes to heat pump installs. All right, so I just want to put this into perspective for you. And if you are a heat pump installer or even doing designs for installers, you have a massive opportunity to impact your client's life, both hopefully for the better, but you can definitely do it for the worse too. So if you do just follow or don't spend this 1 hour of design work, you can really burden your client with an uncomfortable temperature that they need to live in, and that is accompanied with high bills as well. So that's not the reason they would have got a heat pump. They would have wanted the opposite. Whereas if you do spend that 1 hour that maybe you're not used to doing, for your customer it makes obviously the world of difference. So first of all, they're living in a comfortable temperature and they're not using as much energy and they're not paying for as much energy. So I just want to highlight here what a difference you can have on your client, and that impact will just flow on into the rest of your business too. If you're having clients like this guy on the left, he's going to be telling all of his neighbors, which is, I suppose, what you want to grow the business. And I hope that sets the scene well. So really just wanted to, before we go into like the actual design examples and the processes, I wanted to just set the scene that how important heat load calcs are and really how it benefits everyone. So it benefits the homeowner, like we just saw. It will benefit your business to have happy customers. It benefits the climate, and it benefits the industry as a whole. Whereas if everyone's doing the opposite is happening. Like the whole industry is looking bad. No one's making any money. Clients aren't happy either. And the rollout of the heat pumps are definitely going to slow down. So cool. What we're going to do now is a bit of a looking at using the award-winning project as an example. We're going to go through an example project and pick out the key steps that you've got to go through to design this efficiently. And like I said before, we're essentially doing two designs. We're going to keep doing the average one and the award-winning one, so you can really highlight or see the difference between the two. And for simplicity, we are just focusing on heating for this one, rather than doing double the amount of calculations, but it all still applies. Okay, so there's 4 key parts, and yeah, you might have been to some talks on these individually too, and hopefully this will go into a bit more of a real-life example. So there's 4 steps. First one, got to do your load calculations, keep saying it. And then that's not everything though. There's 3 more steps that you need to go through that will help or make sure your system is actually efficient. So heat pumps aren't suitable for every building, which is why you're hearing a lot about envelope and fabric upgrades, which we'll go through second. Once you've gone through those 2 steps, selecting the right equipment is important too. So just like I mentioned earlier, oversizing doesn't help. So if you do the world's best load calculations, you even improve the envelope. If you then get a little bit nervous and want to oversize, you're just undoing all your good work. So just something to be aware of. And finally, you've got to actually install it as per the design and size everything accurately, and also make sure it's balanced. So yeah, we'll go through the load calculations first. So this is the average designer, and it's actually quite concerning that I got this example from Googling how to do manual J calculations and seeing what came up first, and it was this. It's really worrying. If it's top on Google, I think everyone's clicking on it and using it. But so what it's saying here as this rolls through is, first of all, it recommends doing the area calc. So I just roughly took the 2 measurements of the area. I'll explain as it starts again. So in the blue, got the 2 dimensions of the 2 main parts of the building, timesing it by 10 for the height, and whatever the answer is, turning that into BTUs. Then add 1,000 BTU for every door or window, which with there being 15, that's 15,000 BTUs. So this gives, if you follow what Google recommends here, it's recommending that you need 69,000 BTUs for this system, which, I mean, spoiler alert, it's not right, but we'll see that next. Okay, so this is what the award-winning heating engineer did. So first of all, use the right temperature. So based on the address, what does winter actually look like? And then very important, what materials is the building built out of? If you don't have those 2 bits of information, like how well insulated the building is, where the building's located, you can't get accurate calculations. So I will talk through this in a second, but I suppose just to reiterate why the temperature is important and the materials are. If we go back to the average example, if that building was in San Diego or Miami compared to it being in Colorado, that's not factored that in terms of the temperatures. So how can that be accurate? It's not looking at it. And if you've not actually looked at the windows, triple glazed, single glazed, again, how can it be accurate? So what's happening on this one, as we saw at the beginning, and maybe I'll just let this come round again. So putting in the address, that's finding from the local weather station, external temperature, which based on Denver, it's picked 8.6 Fahrenheit. And then just reviewing all the materials there. So what are the doors made of? Is there insulation on the walls? Then you are doing an area calculation. It's still part of it, it's just the way they did it before wasn't correct. And then putting into scale all the doors and all the windows too.
Quick question.
Yeah.
Are the insulation R values and windows and all that, is there a default for code year built that you can just throw in?
Yeah, there's a list of defaults, and then yeah, you can build your own too.
Okay.
So.
Is there an automatic default, like one code year built, like just like overlay everything?
Yeah, there is. So yeah, you can pick like what age of the building is as well. So the older the building, the more it's going to look at like extra air changes, yeah, worse materials.
Can you put in different like use types for like airflow, air exchanges?
Yes, you can. So I mean, to make this quick, I just drew one big living room, but yeah, you can draw like kitchen, dining room, and this is a domestic or residential example. This gets used for commercial too. So yeah, huge buildings.
What software is it?
It's called H2X. Yeah, we're in the exhibit hall if you want to come over. But I suppose this is what we'll be looking at throughout a lot of the presentation. And just to finish this off, when we zoom in, the total heat load is 158,000 BTUs, I think. Just more. So if we just do a quick comparison after the first step of the load calculations, pretty easy to see. Well, with the colors as well, but for the average designer, they've found a 5.9 ton heat pump will be sufficient, but in reality that's massively undersized. We've just realized it needs to be 13.2, but they don't know that, and they're never going to find that out until they turn it on, which is way too late, and it's going to get worse, as we'll see. Whereas for the award-winning designer, he's correctly sized it, so he can tell his client straight up what the energy usage is going to be. Like I said before, not every building is suitable for a heat pump, so definitely more energy efficient buildings reap the benefits of it. Which, if we go to the next step, is the envelope improvements. So yeah, with this one, we're going to do the same approach, look at the two different strategies. There has definitely been a lot of talks about this at the summit, so hopefully you're all aware of how important this is, but a bit of an analogy, if you've got a bad fabric, so if it's like an old building, it's leaky, bad windows, no insulation, it's almost like filling up a bucket with water that's got a lot of holes in it. You're just going to use a lot of water to keep that bucket full. Comparatively, if you improve the envelope, you're essentially sealing all those leaky parts, and you're going to use less water to keep it full. It's still going to get out slowly, but I suppose, yeah, lowering that amount is key. So a bit of an easy one, if we look at the average designer here, they're not used to recommending any improvements to the fabric, and because they haven't even factored in the materials, how can they go to the client and recommend? If you change to your window, it's going to be worthwhile because of whatever reason. They're just not in a position to do that. So I suppose that's the importance of having your calculations, because it's the base of everything moving forward. And with this one, so this is the award-winning installer now. So they've identified that a lot of these materials are old and not the best for heat pumps. And that's going to consume a lot of energy for the client. So what they're doing here is simply going through, changing the doors, changing the windows, adding insulation, and we can see, went a bit fast, but we started with 158,000 BTUs and reduced it to like 50-something thousand. But just to show you how easy it is, just change those. They've got different R values, different U values, and straight away when you click done, it just runs the calculations instantly. So yeah, it brings it right down. So really here, you're just putting like a jacket on the building so it's not losing the heat as fast. And because you've done your calculations, you can actually really impress your client by giving them some information to impress them. So here you can say before we made any improvements, you're using 158,000 BTUs per hour, and annual energy of that is 116,000 kilowatt hours, a significant amount. However, you can go to them and say, okay, there is a one-off cost. You need to replace your windows and add insulation. It's going to cost you money, but it's a one-off cost, and like materials generally are much cheaper than energy in the long term. So it is worth doing most of the time. And as we can see here with the after one, we've made the upgrade and first of all, reduce the total heat loss on the left-hand side here from 158,000 to 54,500 BTUs. And annual energy consumptions come down from 116,000 kilowatt hours to 40,000. So when you go to your client, you can tell them, okay, there's going to be, I don't know, $20,000, $30,000 of maybe fabric improvements, but the annual energy saving is significant. And I didn't run the calc for this because I didn't know the cost of all the materials, but it'd probably pay back in 2 or 3 years.
Can you put that in if you have it? Like all your recommendations, can you compile the cost per measure?
You can download like Word documents that summarize it. So I suppose you can customize it in like Word then to say like we recommend this. But yeah, you can download like multiple options like this where you've got, here's the before, which is going to be like a 13-ton heat pump, or like after where there's going to be a lot of cost. Not even that you're making money on usually, but just showing you've got the best interest at heart, that we can actually get you down to a really small heat pump. So just taking a look at the results again, looking at the average one. So just to remind ourselves, he didn't look at any weather data, he didn't look at the materials properly, he did a lot of rule of thumb, and that's resulted in a 5.9 ton heat pump, should have been 13.2. And then when it's come to, arguably that's not suitable for a heat pump just because the energy usage is so high. It loses its benefits, but they've gone ahead and they're going to be recommending this anyway to the client. Whereas the award-winning one, correctly sized, but then because they've correctly sized it, they've been able to design a really economical building for their client. Like being able to demonstrate to them that, if you use me for this job, I know exactly how this is going to work, and I'm able to get your heat pump size down to this and lower your bills, which is probably what they want. All right, so the next step now is the equipment sizing. And there's a few different approaches to doing this. Like I said before, very important your load calcs are correct and your envelope improvements, because it does need to be accurate. Dissimilar to furnaces, where if you oversize, it's going to be okay. Not the case with heat pumps. Haven't really put any slides talking through that, but they're just designed to be on lower temperature, more usage, whereas gas furnaces, more just on and off, fast response times, which is why the oversizing doesn't work. And this is just for illustration purposes only. It's not based on any manufacturer specifically. It's just to show now that how we choose the heat pump affects the coefficient of performance. So down the bottom here, we've got the heat pump size, increases in tons the more it goes to the right. And on the y-axis going vertical, we've got the SCOPS, which is the coefficient of performance. Generally, the rule of thumb is that in a heat pump, the compressor has to work harder the more load that's on it, which is demonstrated by this like yellow-orange line. So as the heat pump size gets bigger, it generally struggles to achieve the same performance coefficient as a smaller heat pump does. We'll go more into that in a second, but just to use this, first of all, if we plot our average designer's heat pump on here, so 5.9 tons is what he thinks, or they think it's going to be at. That intersects with the line there, and as we go across, it achieves a 3.8 SCOP. Not bad at all. So that would be turning every kilowatt into 3.8 of heat output, which is pretty good. It's definitely not terrible. Problem is, didn't do the heat load calcs properly as we went through. So his performance is like off the chart in this one in a bad way. He might not even do 2.8. It's kind of hard to fit it on this, but The SCOP is really low there, and you might think it's still turning 1 kilowatt into 2.8 of heat output, but electricity is more expensive than gas, and they're investing quite a lot in this system, so they're going to be very unhappy if they get that installed. And there's more to come yet to show it probably wouldn't even operate at that. Comparatively though, first of all, just on the face of it, the award-winning heat pump designer, if we plot 4.5 tons there, they're getting 4.1 SCOP. So again, it's good. Anything above 4 I think is good, what people aim for. So every kilowatt that goes into it, you're getting 4.1 out of it in terms of heat output. Generally at this size, smaller it doesn't really make sense, but when you get to around 4 tons and definitely higher, it becomes more efficient to have what's called cascade heat pumps, which is just like a fancy word really for saying having 2 heat pumps connected together. So instead of 1 big one, 2 small ones, and they share the load between them. When it's at a small tonnage, it doesn't really matter because it's negligible differences and it's not really worth the cost. Sorry, yeah?
In the cascade design, are the 2 systems serving the same square footage, or are you dividing the space? Like you just have a portion of the home served by reverse heat pump and a portion of the home served by the second?
You can do it that way, or they can just work together, so essentially combine to 1 pipe, and then it's kind of like 1 system within the building.
Yeah, I think it's important to know that's like probably most applicable like water source systems. Right, like air source wouldn't probably work that way, I'm guessing.
Air to water.
Air to water.
Air to water, you do that all day long.
Yeah.
Yeah.
There's cascade, it's lead and lag.
Yeah.
So we're gonna have the lead this guy's gonna do, and it's based on, it's gonna pull in on the other one
Yeah.
to offset that load of the home. Same exact thing, it's modulating turn down ratio on boilers, on hydronic, on high efficiency boilers.
Yeah, and I suppose if you're doing a new build, the cascade, I suppose sharing the load makes sense, but you could, if you've got like a gas system that does a lot of it, you can just have like a supplementary heat pump as well, or the other way around. But I suppose just to demonstrate, if you did put them together, very simple, reduces the load by half, assuming they're doing 50-50, and as you can see here, got a 4.5 SCOP. So turning every 1 kilowatt of energy into 4.5 of heat output, and I suppose remembering this is the 450% efficiency that we mentioned at the beginning.
Just to clarify language use, SCOP, is the same COP that we use, or is it a seasonal COP, is it a different metric?
System.
Yeah, coefficient of performance, it's like averaged out over the year.
We just use COP.
Yeah,
So it's
okay.
the same.
It's the same, yeah. Yeah. Cool. All right, so if we just take a look at the results again now, so things are going bad to worse for the average designer. Way undersized, load calcs didn't do them properly. Didn't recommend any envelope improvements, so arguably the building's not even suitable to have a heat pump. And then on top of that, they've got a really low performing heat pump too. That, I suppose we're talking about the coefficient of performance here, but undersizing a heat pump that bad is just going to create a load of wear and tear, and it's not going to last as long as if we compare it to the award-winning one, where it's all designed perfectly and it's going to operate in its optimal zone more frequently. I mentioned at the beginning that this award-winning use case was a hydronic system.
In floor.
Partly in floor, partly like radiators.
And concrete, not stable.
Yeah.
Based on 100-degree water temperature at what outside?
Outside, we get to it in a little bit. Outside in Fahrenheit, the average is 40 Fahrenheit.
Is what?
40 degrees Fahrenheit.
40 at 100 degrees water.
Yeah, that's been the average so far. So yeah, the use case was based on a hydronic system or air-to-water heat pumps. Most of the things I'm going through here today are very applicable to air-to-air as well. So in terms of doing your heat load calculations, doing your envelope improvements, correctly sizing your equipment, maybe not the cascade part, but all things you should be doing as well.
In this award-winning thing, are you having a backup electric boiler?
No backup electric boiler. So in terms, just a heat pump, it provides all the heating, and there's a diverter that provides all the domestic hot water too for the water heater. All right, so I suppose if we move on to the last part of this, it is now sizing and balancing the system properly. So if you hadn't, even if you've done all the 3 steps before correctly, which is more design, if you get to the site and you don't install it properly, and really by that suppose I'm mainly talking about the balance inside. So like the air will try to take the path of least resistance. So the room furthest from the air handling unit is going to be quite hard to get there, whereas the closest room, the air is going to want to go out there. So you need to make sure you balance your pressures so that everyone in all the different rooms are, I suppose what you're trying to avoid is someone saying they're too hot and someone saying they're too cold, because that means the heat pumps are overworking once again. So if we look at an average designer, pretty typical that, especially if it's a building size that you've done quite often, the sizing might be just done based on the last job or maybe what the manufacturer recommends. Maybe that's not the worst thing, but what is terrible is if you don't do the balancing properly, because it leads to that uneven heating throughout the building, which is going to add an extra load on the heat pump that all your calculations of like usage and power output aren't taken into account. Whereas taking a look at the software now, so this is moving pretty fast, but what's happening here is they're distributing the flow rate equally. So they're actually drawing out the system of what they plan to install. This is a supply and extract. So they're drawing it out, and because they've done the load calcs, the flow rate is coming into the diffusers and the grills. And what's really important is, although it's sizing the fan for like to get to the most disadvantaged part of the system, it is making sure all the pressures are equal. So as this goes through again, sketching out the proposed ductwork layout, as they go around and drop on the grills and the diffusers, it's assigning the flow rate to make sure the building gets the heat. When it sizes everything, you can see velocities, pressures, flow rates, the sizing. Most importantly, what you want to see is that all the pressures are equal. So through what we call dampers, like balancing devices, it's making sure that as it branches off, everywhere's getting equal pressure. So this can be done on site. It's much harder to do accurately because you're running around every room, making sure it happens. So yeah, all right. So that's all the 4 steps that we've been through now. So I probably don't need to go through this again. As you can see, like things just aren't really going well if you take the average approach. It's just really inefficient, uneconomical. Things are undersized, and the opposite's happening for the award-winning one. Doing things accurately, things are being sized accurately and will work as intended to. And I just wanted to put this into some results at the end. So just to summarize this, the annual energy in terms of heat output for the average will be 116,000 compared to the award-winning one, reduced massively down to 40,000. Because the SCOP is pretty poor for the average one, that means that annual energy usage is 41.4 thousand. That's what they're paying for, and that's going to be $8,280 for the year. So for the award-winning one, lower annual energy consumption, higher SCOP as well. So for 8.9 thousand kilowatt hours, they're just spending $1,783 on the bills. So obviously a massive difference there. There was an initial cost difference for putting the insulation on the building, but in a few years it will pay back. And then here's the real-life data from the award-winning design. So yeah, this was the hydronic system. So it's floor heating down the bottom, radiators on the upper level. And so yeah, it's been operating through winter in the UK, as you can see down there. 4.5 is the coefficient of performance on the left, and all the details up above. So circled in green, it's consumed 153 kilowatt hours, and it's actually generated, in terms of providing heat, 689, which is 4.5 times higher, which is the coefficient of performance. I didn't highlight it, but yeah, the average outside temperature has been 45, I think I said 40, and the average flow temperature has been 84. But it was designed for peak demand would have been 100 Fahrenheit for the flow temperature, and outside would have been around 30, I think.
Can I ask how you're measuring heat output?
Measuring. So this has come from a public website. I can't remember what it's called. But it monitors all the heat pumps in the UK, and you can go on there, and it's pretty much like a leaderboard of different efficient heat pump systems. So they've got controls that measuring all of this. And yeah, I mean, the award-winning heating engineer just sent me a screenshot, and yeah, I put it in. I don't know if it's required by code, but But I'd say it's required to be, because if you don't set it up this way, because you're designing for worst case always, which is like peak winter or peak summer, if you don't have the weather compensation, then you're gonna be working too hard when it's not that peak day, which is most of the time. So this allows it to scale up and down. The manufacturers providing the equipment should be able to like, help with a lot of this. Should. But yeah, okay, well just to finish off then, there's just one key takeaway from this presentation. Just really want it to be that you should be spending a bit more time than the average on the actual design side of it and the heat load calcs. You really do get out what you put in. So you put in a bit more time, you'll get out a way better performing system. And then just to summarize the key steps, do your heat load calculations accurately, which I've said a few times. Definitely advise on envelope upgrades, and I mean if you don't need any upgrades, and I think even just letting the customer know you've checked it is a really good thing to do. You've got to correctly size the equipment, no oversizing, no undersizing, and then finally making sure the system is balanced and operating as you've designed it. So you want the flows to go where you want them or where you've intended them to go. And I suppose, yeah, this is just a flywheel for your company. So if you're doing things well, happier customers, hopefully you're winning more jobs and yeah, just building a better business. It's the idea behind it all. And yeah, I suppose that's everything. So thanks for your time. I hope you found it beneficial. I will do a Q&A, but I am here representing hvac, which is the design software that we've been seeing at parts of it. We are in the exhibit hall. And I do have a quick video just to show you. They might answer some of your questions that you have, and after that, yeah, I'll take some questions. So let me see if I can get this full screen. Okay, so it's just 2 minutes just explaining it. I think the blur will go in a second when it loads, but you can upload the blueprints as the background. So upload those in if you have them. If you don't have them, we have a LiDAR scanner coming that you can go to a building, scan the room, and it will populate what you see in here. Or alternatively, you can, a bit more traditional, if you want to go and take measurements in a building, you can just use that dimension tool that you see here to build it all. So that's doing your load calculations based on like the temperatures and the materials that we saw earlier in the video. And then because we have that as the almost behind the system, you can now move into the design stage after you've done like your manual J calcs. So as you place heat pumps, and this example is a hydronic system here, or you can place air handling units. As you're drawing your pipes or your ducts, it's able to recognize the load calculations that you're drawing on top of. So it's going to evenly or proportionally send out the flow rates to the different parts of the system. So here it has auto-populated it, but just want to show you can override everything too. That means then when you click results, it's got all the information to size everything for you. So you've got perfectly sized system just from drawing the layout. All the calculations have been done in the background. So you can see velocities, pressure drops, flow rates if you want to get into the details. But most people, care about the actual sizing, and it does also size your fans as well. Hydronic system, size of recirculation pump, and there's a lot of information on like index circuit length, system volumes, and things like that. And then because we've drawn it out, it provides a great platform now to export into different parts of your workflow. So you can send drawings with your logo to your client, to the team on site, to help win more jobs and help install it. It automates the takeoff, so all the bill of materials, and then all the different reports for different manual Js and other things, all for people to review. I suppose you can pay monthly, so you can turn it on and off. Would be the only way. If people aren't doing one project a month, generally it's probably not worthwhile for them. But if you're doing more than one or more projects per month consistently, the benefits compound. Yeah. Sure.
Radiant floor layouts?
It does, yeah. Yeah, so it'll do all hydronic system from pipes, radiant floors, and like any other heat emitters too.
It'll calculate out BTU output of radiant floor systems?
Yeah. So choose your floor material, choose your water temperature, and it will tell you what spacings you need to achieve that output. Yeah.
Just a couple easy ones, I think, but can you do, so if you have a multi-story, like just residential, can you do like VRF or anything with heat recovery?
Yeah, so I suppose we've got heat recovery is a big part of it actually, so you can put that in.
Okay,
And,
then, is the manual J, is that like ACA, whatever, like certified so you can use it for permitting?
So no, it's not ACA approved. We started the process. It's quite a long one. Probably say in 2 to 3 months we'll have that. It might not mean too much here, but CIBSI, who are like an ASHRAE equivalent overseas, have verified a lot of the calculations independently, which we've got certificates for. So I suppose hopefully that will give you confidence it is correct on top of like all the thousands of projects people have done. But no, ACA approval is coming soon. Yeah, I mean, we've got a full case study for it actually. Let me, it's all public. I mean, the designer's really proud. Yeah, he's won an award for it. If you actually search award-winning heat pump design, I think it comes up top on Google, but on our website, if you go to case studies, this is the design. So it was an old building. I can't really read that from here, but pretty much goes over the project, goes over like technical challenges, which like a lot of what we went through today, it's all old, bad materials, oversized system, and yeah, made a lot of improvements. So first thing, building envelope upgrades. So did the heat load calcs to do that properly. And then yeah, just put in efficient systems, did the cascade heat pump, and he did use a NEBI system, which I don't think is over here yet. No, it's it's just like a hydronic heat pump.
Like R32 being the refrigerant, or?
Oh, I'm not sure what refrigerant's inside it.
R290 is really popular in the UK, and it's not
Yeah.
possible.
Oh, is it not? I'm sure if you go on their website, they'd have all that information. Well, yeah, if there's no more questions, thank you. I appreciate your time.